Welcome to the final video on vector calculus in our course. We're going to talk about the three major theorems, Stokes' theorem, divergence theorem, and Green's theorem, and unify them all together as part of a common picture. So the first thing to talk about, if I have a vector field like this one, is that there are two local properties of a vector field we've talked about, the curl and the divergence. And what I mean when I call these a local property is at any single point in the domain, you can compute out the curl and you can put out the divergence. It's something that is true around a specific point. Curl gave the tendency for the field to sort of spin around some particular axis, and the divergence gave the tendency of the field to be separated away from some point in a nearby region of that point. Both of these are local properties. We can contrast that with some global properties that we've seen in vector calculus. For example, I'm going to put up a two-dimensional and three-dimensional pictures of the same story. In the two-dimensional case, I'm trying to figure out the flux across a particular curve, the tendency for the field to leave the curve, or in other words, the tendency for the field to be aligned with the normal vector to the curve. And the same story is true in three dimensions. If I have a closed surface and I have normal vectors leaving from that surface, the question is, to what degree is the yellow vector field F leaving or spreading out across that surface? In other words, aligned with the normal vectors. These are global properties. They're about entire curves or they're about entire surfaces. And then the two theorems we saw about outward flux was Green's theorem in its divergence form and the divergence theorem. Both of these computed the outward flux. In Green's theorem, it's the outward flux across a curve, and in divergence theorem, it's the outward flux across a surface. And then what's core about these is that this property around the boundary, what I'm going to call a global property, could be equated with adding up or integrating a local property of the divergence throughout the entire region. So in the case of Green's theorem, the region is some area, and if you add up all those local properties, the divergent at every point inside of the domain, you get the global property of the outward flux across the boundary. Similar for the divergence theorem. Your closed surface now encloses a volume, and if you add up that local property of the divergence at every point in the volume, it's going to add up to the global property of the outward flux across the boundary of that region. So the key takeaway here is that this accumulation on a boundary could be expressed as adding up a local property, in this case the divergence. So the divergence of F was one of our so-called differential operators on F. But we had a different one, which was given by the curl. We have a similar story there. So we have a two-dimensional case and a three-dimensional case. In the case of the curve, we're now trying to measure the circulation, which is the tendency for the vector field to be aligned with the tangent vectors. And similarly, if we go to the three-dimensional situation, you could have a surface that has a boundary curve, and we're asking what is the tendency for the vector field to be aligned with the tangent vectors to that boundary curve. And just as with the Green's theorem and the divergence theorem, we have a similar relationship with the other half of Green's theorem, called its circulation form, and Stokes' theorem. And they're both talking about the counterclockwise circulation, either just around the curve in two dimensions or around the boundary curve of your surface. And really what they say is, again, this property around the boundary can be written as adding up the local property of the curl, or kth component of curl for just in two dimensions, but either way, adding up this local property over the entire domain. So in the case of Green's theorem, the inside of that region in the plane, and in Stokes' theorem, it's this curl dotted with n all along the surface. So again, the big thematic takeaway here is we have another one of these local properties expressed as a differential operator. It's the curl of our vector field. And then adding up the appropriate proportion of that curl, of that differential operator, over the entire domain gives us this property along the boundary. Okay, so let's see how far this pattern goes back, because we actually saw a little earlier in the course something called the fundamental theorem of line intervals. This was a measure of the flow along a curve, but it was specifically for when you had a vector field that could be written as the gradient of F. We've had the divergence of a field, we've had the curl of a field, and now we have this third thing when a field is written as the gradient of a scalar potential function. It's sort of a different type of differential operator, a differential operator on the scalar potential function now. Now, the boundary of a curve that has endpoints is just the 2 points, those two endpoints. The boundary is a little bit simpler. And yet, once again, we have a similar kind of local to global transition. When you integrate a differential operator, so in this case, we're integrating the gradient of f, and we integrate that over the entire region, you just get some result on the boundary, in this case, the two endpoints, f of b minus f of a. And this could be pulled back even further to the fundamental theorem of calculus 2, which said that if you have a differentiable function, when you integrate the derivative is perhaps the simplest of these so-called differential operators, something that acts on a function by taking some type of derivative, then the integral of this derivative is just some information about the boundary points only, f of b minus f of a. So really what we've seen is that basic theme is consistent from the fundamental theorem of calculus back in single variable calculus up to the fundamental theorem of line integrals, and then our big theorems of Green's theorems, part 1 and 2, Stokes' theorem, and the divergence theorem. So putting this all together, I'm going to write down a unifying principle, which says if I'm going to be integrating a differential operator over the entire domain, then this adds up to a measurement just along the boundary of that domain. Exactly how you interpret this sentence depends on the context. As we've seen a few different ways to interpret this depending on what kind of object we're talking about. But the basic idea was always this idea of adding up a differential operator over the entire domain gives us some information about just the boundary. And indeed, sometimes we focus more or less on the proofs of these different statements, but all of them actually do rely on the fundamental theorem of calculus 2. And one of the ways we can think about this is that all of these big powerful theorems of vector calculus are different types of generalizations of the fundamental theorem of calculus, depending on what the context is. So you take the basic fundamental theorem of calculus 2, and you generalize it to these different types of concepts, and you get these different theorems of vector calculus.